All right, Calculus 12, here we go. A nice overcast May day. More trig. 7.4, applications of trig. Derivatives. So here we roll. To be honest, this is actually in class. I would very much let the students, you people, do these questions on your own, because you actually know how to do all of these. Because really, it's just a matter of keeping all your trig derivatives that you know that we've learned in this unit. And then now it mixes with related rates, max mins, velocity, acceleration, displacement, and local approximations. So basically nothing new, in all honesty, except just knowing that the derivative of sine is cos, derivative of cos is negative sine, and so on. And not forgetting any of your derivative rules to boot. So, to be honest, I feel doing these, it's just me doing them, which is good, but really I'd really like you to do them. So but at the same time, I don't know how to online make you do them and sit there and observe. I can't, it's impossible. So here we go. First question is: a spring moves up and down vertically with the position of the block at the bottom of the spring given by h of t is 3 sine t plus cos t, where t is between 0 and 2 pi. H is in meters, t is time in seconds. Find the times when the height is a maximum. So, got a spring like that with a block on it. It's moving up and down. Just imagine pulling that, and then if you let go, it'll go up and down. Now, in theory, it would over time dampen. So this would actually be multiplied by some kind of exponential decay, which would be like ideal situation. But assuming this goes up and down, and especially in that small time frame, there'd be very little time for dampening. We're assuming it's going to go up and down at a constant, not a constant rate, but it's not going to be dampening over time due to effects of gravity and friction and all that kind of fun stuff. So there's the position function. Wants the maximum height. They could have asked, this question could have asked so many things. It could have asked for velocity at a certain time, could have asked for maximum velocity, maximum acceleration. It could have went into so many different levels, but they wanted the maximum height. So maximum, so as soon as you see maximum or minimum, you know it's going to be a max-min problem, which then needs a derivative, and the derivative then needs to be analyzed for its critical numbers, and then the critical numbers need to be analyzed with the first derivative test, which then need to be analyzed to see if they are max or mins with increasing and decreasing. You could even go to the second derivative and do a second derivative test, but that's not worth it. So here we go. Derivative. So the derivative of 3 sine t with respect to time is going to be 3 cos t. Derivative of cos is negative sine. So it'll be negative sine t. So there's the derivative, which now, because I'm doing max-min, I'm thinking critical numbers. Are we on the screen there? We are, okay. So critical numbers happen. When is the derivative equal to 0? When is the derivative undefined? And are there any endpoints? So let's go backwards. Endpoints, definitely at time 0 and time 2 pi. Is there any does not exist situations? Well, there's no denominators equaling 0, there's no square rooting, there's no logging, so there's none there. And then the question comes, where is 3 cos t minus sine t equal to 0? And like the irony of it is, the only calculus really is right here, to be honest. So how do I solve this? Well, I don't see any trig identities, because there's no squareds and there's nothing special there, but I see a trig identity in the works. If I sine, so 3 cos t, move the sine t to the other side, divide by cos, you'd get 3 sine t over cos t, 3 equals tan t. And now you can solve this, which is an equation. It's positive, so we know, I would do this with my cast rule, I know it's going to be in quadrant 1 for all suckers take, and quadrant 3. So my first time would be right here, and I'll call that time 1. It's really an angle, but it's a time as well, and that's time 2. To find my reference angle, this is not a special ratio at all, so I'm going to have to go to my calculator, which in all honesty, you know what? I don't even feel like using a calculator, because why make life hard on myself? I'm going to call it TR for the reference angle. The reference angle is going to be inverse tan of 3. That'll be some angle between 0 and 90 degrees. Good for it. My calculator would just spit out a number if I was in degrees. I'd leave it in radians just because the answer was here. But you know what? Don't feel like using the calculator. Makes it easier. So what's my time 1? My time 1 is going to be this answer. Inverse tan of 3. What's time 2? Time 2 is going to be pi 180 plus the reference angle. And in university, if your prof doesn't allow you a calculator, that's how you would leave answers, so to speak. So there's my 2 potential critical numbers and my 2 endpoint critical numbers. To find maximums, then we need to go to my first derivative test. And you might wonder, well, how am I going to do the derivative test if I don't have exact values? Well, I'll show you how I would do it. I find no calculator actually easier in some ways. So there's my endpoints. This I know, again, just giving me some reference. There'd be pi. Here'd be pi over 2. Here'd be 3 pi over 2, just to give me some reference. I know this first answer was between 0 and 90, so somewhere in here there's a 0, and that would be my time 1 of arctan or inverse tan of 3. And the other one is going to be in quadrant 3, which is between here and here, so it's somewhere in there. There's time 2, pi plus arctan of 3. Now to test my intervals, remember this is my first derivative test, so I'm going to my derivative of height. So I would probably plug in, I could even probably plug in 0 because 0 is an endpoint, but let's plug in a number a little bit bigger than 0. Let's plug in, I don't know, 0.1-ish. So here's my derivative. Think about for a minute, what's cos of 0-ish? Cos of 0 is 1, so this would be 3-ish. Sine of 0 is 0-ish. So this would be 3 minus 0, which would be positive. So this is going to give me a positive value. The function is increasing from 0 to my first time. Here I'd probably plug in pi. Like, why not? Make my life easy. And I know pi. So going over here, cos of pi, I personally have to think about my cos graph. That's just me. There's pi. Cos of pi is -1, so this would spit out a -3. Sine looks like this of pi is 0, so it'd be -3 minus 0, so this is a negative value, so the function is decreasing, so this must end up being a maximum at that particular critical number. And then sure, I'd plug in 3 pi over 2 for the other interval and use this graph to help. Cos 3 pi over 2 is 0, so that's 0, and sine of 3 pi over 2 is -1, so this would be giving me a positive value because that'd be negative. And so it's positive value. So now what do I have? I have a starts here, goes up, so this is a minimum, goes to a max, so there's a max at time 1, and that max height would be h of t1. And then it goes down to a minimum, which I don't want. I just want maximum. There's a minimum here, minimum there, max there. And it would also have a max at time equals 2 pi, h of 2 pi. All right. And I could even plug in these values into here. Like I can actually even find this if I wanted to, just to show you just how clever a person can be without a calculator, just to make them life. Because sometimes people think, oh, I have no calculator, I can do nothing. That is not true. Just some no calculator thoughts here for a minute. So it's a little bit of an aside, but I think this is the most important part besides the calculus. So I know that tan t equaled 3, which is 3 over 1. This must be my y, that must be my x. Then I know the radius, remember from pre-calc 11 and 12, must be x squared plus y squared equals r squared. So I know this must equal the square root of 3 squared plus 1 squared, because if I think of my picture for a moment, this would be opposite adjacent. This side here then must be root 10. So I actually know, sitting at that picture there, I know if this is T1, I know sine of T1. Sine of T1 is 3 over root 10. Cosine of T1 is 1 over root 10. So if I wanted to go back to the original function, if they wanted me to actually give you the height here, height of T1 would equal 3 times 3 root 10 plus 1 over root 10. And that would end up giving me 9 root 10 plus 1, 9 over root 10 plus 1 over root 10, which would equal to be 10 over root 10, or root 10. And then the same thing for the height at 2 pi. Could easily do that. Sine of 2 pi is 0, so that's 0. Cos of 2 pi is 1, so that would be 1. And this would be meters for both. But I went way above and beyond because the question just wanted what are the times. The times are T1, arctan of 3, and pi over 2. Sorry, 2 pi. All right, that's first example. Second example is two sides of a triangle have the length of 15 and 20. The angle between the two sides increases at a rate of pi over 90 radians per second. How fast is the third side changing when the angle is pi over 3? So as I read that, as soon as I see things that are changing, I'm like, this is related rates. And I need some relationship. And obviously a picture would be very helpful here. It just tells me there's a triangle with sides 15 and 20 and some angle between that is changing. I am not going to put that angle in there yet because this angle is growing. This is fixed, that is not. And it wants me to figure out how quickly it wants the change in x, how quickly that side is changing at the instant the angle is pi over 3. Knowing that the change in the angle is pi 90 over pi. Just one thing, just to be aware, now when we're working in trig mode, anytime you have an angle with change, always use radians per second, or always use radians. Don't use degrees. Because degrees have units, and because radians don't have units, it'll make your unit analysis horrible with degrees. So, what relationship links these? It's not a right angle, but it's got a, I would say that what links these together is cosine law. You can see that you have, so a squared, so x squared equals b squared plus c squared minus 2 times b times c times cosine of the angle. So that's cosine law. Look that up. It's been a while. I know it really fresh because my pre-calc 11's just finished it. You haven't done it in a while, or maybe you've done it recently in physics. I would do a little bit of cleanup on this before I took the derivative of it. And I would ask myself, is the derivative even worth it? So let me just clean. So 15 squared, I should do it in my head, but 225 plus 400 is 525, but I just want to verify for my own long day. Oh, 625, see? I would have been off by 100. 625 minus, and then you get 2, that's 50, that'd be 600. And then at that point, what are we going to do? We need to ask ourselves, is the derivative of this worth it? If I took the derivative of this now, I'd get dx dt's and x's out. That's fine, because I want dx dt. I can find x from this if I had to. And I would get d theta dt's out. That's fine, because I would have that. So let's take the derivative. Derivative of x squared with respect to t is 2x dx dt. The derivative of a constant, thank goodness, is 0. The derivative of this is going to be negative 600 times the derivative of cos. Derivative of cos is negative sine theta times the derivative of the inside with respect to time is d theta dt. Biggest miss right there. So you get a double negative, makes you positive, and solving for dx dt, dx dt would then equal, so negatives cancel. When I divide the 200 over to the other side, 600 divided by 2 would be 300. sine theta d theta dt divided by x. And now I have everything I need to plug into here because it wants me to do this at pi over 3. So 300 times sine of pi over 3 times the rate of this, which is 90 over pi, divided by x. Oops, x is the only thing I'm missing. But remember, I have x back here because x equals the square root of 15 squared plus 20 squared minus 2 times 15 times 20 times cos of pi over 3. Can I do it without a calculator? Well, 625 minus 600. Cos of pi over 3, cos of 60 is a half. So this would be 300, this would be 325. Now if I didn't have, is that a nice number? Nope, that's okay. Leave it like that even. So I can actually just plug that into there. Why make it messier? Sine of pi over 3 is root 3 over 2, so I get 300 times root 3 over 2 times pi over 90 over that mess. What can I do for cleanup? I could probably do a number of things, but that would be a legitimate answer there. It's just not the easiest to look at. Obviously I can run to a calculator. Well, running to a calculator is kind of the cheat way out, but you know what? Sometimes you just go with it. Let's just see what this is. Times pi divided by 90, all divided by root 325. 0.503 blah 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 blah, and the units on this, because we're finding side increase, centimeters per, and the units were seconds. Could we make that any better? 325 divided by 25. So this could be 5 root 13. Here, that could cancel out. You could get a 3 or 2 canceling into that, making it 15. 3 goes into that 5. So you could have 5 root 3 pi over 3, I think. 5's cancel. And you end up with root 3 pi over 3 root 13, or root 39 pi over 39. Does that work out? I don't know if I didn't work this one out earlier. Let's see. Oh yeah, it does. Look at that. So that would be an answer. It's just kind of ugly. Okay. So that's 2 examples. One was a max min, one was a related rates. You need to, let's see here. I'm going to do 2 more examples if you wish. One of them is going to be a rocket question. The other one will be a local approximation. So I will make that the second video, because if I don't stop now, it'll split the video in 2 and make it a hassle for me.